Okay, so I will start this lecture by the review of Laplace transform. So first, the question is raised, why Laplace transform? So one thing that we know that Laplace transform is useful is that we can use it to solve differential equation. So from ordinary differential equation, but you need to how to say? I need to emphasize that the differential equation must be linear, and it is ordinary. Ordinary means no partial differential equation, but ordinary is like this. So we use Laplace transform to transform the ODE, ordinary differential equation, into polynomial function, rational or polynomial function. After then, we can decompose it into canonical form, and from this canonical form, we can easily find inverse Laplace transform. Then we get the solution. This is one application of Laplace transform. Furthermore, Laplace transform can be used to do the analysis of a system, whether the system is stable or unstable, and we can also analyze a way to design controller. Okay, so Laplace transform is used to analyze and solve ODE. And it's useful because we can simply analyze on ODE by just analyzing polynomial equation. And here is the definition is the integral from So integral from 0 minus to infinity of a function in time, and then e to the minus st dt. Okay, this is the definition. So this is finite integral over time. Then time is removed, so finally you will get the function in terms of s only. Let's see example Laplace transform of Dirac delta function. You can see here the Dirac delta function can be represented by a bell shape like this, or it can be represented by a square like this. Okay. It can be easily shown that Laplace transform of Dirac delta function is 1. Okay. So just go through the integral step by step, and finally you can manipulate it to get this form, and this limit is actually just 1. Okay. And Laplace transform for a step function. So what is step function? Here is the graph of step function. It's 0 all the time from minus infinity to the 0. I mean at the start of operating a system. Actually, when you start operating a system, you set the timing as 0, and the step from 0 to 1 like this. So this is a algebraic notation for step function, and this is a graphical representation, and it can be easily shown that the Laplace transform of step function is actually just 1 over s. Okay, it's 1 over s. Next, Laplace transform of exponential. So we write exponential e to the minus at, or e to the minus at times step function, because we start a system from t equal to 0. Okay? you have a system, you have robot, you have a like steam power generator. When you press a button to start it, you set the timing at 0. Okay, so you have a function h of t e to the minus at. Actually, it's e to the minus at times step function. It means because before that everything is 0. Any parameter, any value is 0. Okay. And then it can be easily shown that this one. The Laplace transform of exponential here, e to the minus at, is actually 1 over s plus a. Okay, a is the coefficient of the exponent of the exponent minus at, right? And Laplace transform of RAM, this one is called RAM, is 1 over s squared. And here, very important, Laplace transform of integral of a function. Let's say you have a function of f of t, but you want to take integral using parameter variable tau. Okay, so finite integral from 0 to t, so no tau will be removed. Then you have a function of time t, right? Because you take integral of this one, you get a primitive capital F of f of t, and you substitute t and substitute 0. Okay, f term of t minus f capital F t of t minus capital F of 0. So finally you get a function of time t. Okay. Then you do the Laplace transform. You transform from from time domain to s domain, and just use integral by part. But anyway, you don't need to see the detail, but you should remember that Laplace transform of integral of a function is actually 1 over s times Laplace transform of the original function. Okay, so it's like this. Let's say you have Laplace transform of a function f of t, and you multiply it by 1 over s. Okay, in the complex domain, in the s domain, then you get Laplace transform of integral of that function. So numerically, if you compute, let's say if you have angular velocity here, and you put the integrator 1 over s here, the output here is angular itself. See? Something like that. See? You have angular velocity here, and then you get angle here. And next one, Laplace transform of time derivative of function. This one is very, very important. It's applied for ordinary differential equation that you have just taken for the assessment. You just have taken. You need to do the Laplace transform of ordinary differential equation, which is to do the Laplace transform of time derivative of a function, right? And here is the key point, that Laplace transform of derivative of a function equal to s times Laplace transform of the original function, but minus the function evaluated at 0. Okay. So if you have 0 initial condition, you only get this one. So it's easy. Let's say if you have h dot and you want to do Laplace transform of h dot, you will get just s h of s, right? Then if you have non-zero initial condition, you still have number from here. That's why one problem is to ask you to find transfer function. Okay. If initial condition is not zero, you cannot find transfer function. You cannot express the term g of s equal to h of s divided by input u of s. You still have something. Okay. You have something. You still have something because of non-zero initial condition. That's why you cannot have transfer function, because definition of transfer function, if you have only this, and if you still have this, then you don't have transfer function. Okay. And so here is a representation by block diagram. If you have a Laplace transform of a function and then you have a block S like this, then the output is derivative of that function. But in practice, this is not. In practice, you do the differentiation. If you want to use transfer function in, for example, in MATLAB Simulink, you cannot just use like that. You need to use approximate derivative. Yeah. So this is just a practical point of view for derivative. So I don't want to explain it too much. The next point is final value theorem. Okay. Final value theorem is to find the steady state value of the output of the system with step response. I mean the input is step function. Okay. I mean you have transfer function, let's say g of s, and the input is u of s. U s, and output, let's call it f of s. So actually f of s equal to u of s times g of s. And you want to find final value of I of t. So final value means t go to infinity. So what is the value of this? For example, if for the first order system, let's say this one is first order. Then the step response, and if u is step, then the output of the system is like this. So final value is here. Okay? And you can find it if you just know Laplace transform of f. If you know Laplace transform of f of t, then you can find final value. Okay? You don't need to solve for the solution in the time domain. This is just an example. Let's say we have angular velocity in second order, because if we look at transfer, you can say you have transfer function is first order, and this 1 over s come from step function u. Okay, you can consider this way. Then the steady state value of angular velocity omega t is given by this. So s time transfer function of the omega, and take the limit s tend to 0, then you get just k. And here is the graphical representation of a system. Okay, because we computed using numerical method, so you get the value just point like that, several points. But you can see the trend of the final value is it go to some constant, right? For convergence of function I have a t, so it means stable system. The final value is called steady state. Okay. That's why here you can see that the notation here is SS. It means steady state. So this table is very useful for you to find Laplace transform and also find inverse Laplace transform. Let's say you have time domain function that looks like one of them in this column, then you can easily find Laplace transform. Or if you have Laplace transform in this form, in one form of this column, then you can easily find inverse Laplace transform. Okay, accordingly. Yeah. So you can see that the Laplace transform take the form of rational function. We call rational function, which means numerator and denominator are just polynomial. Okay? And if you can decompose it into canonical form, you can see from the very beginning. Yeah, here. As long as you can decompose in the canonical form, sometimes you have this, you have like this, but sometimes you can have like s over s squared plus wait, let me show here directly. In some case, when you decompose, you get like this. Let's say if the root of the denominator is complex number, right? You can see here, you put this 1 to 0, and then you can find s actually is complex number equal to alpha plus minus j square root of omega, right? If you have complex roots, you can reformulate as this rational function, and then you can easily find the inverse Laplace transform to be trigonometric function, combination between trigonometric and exponential function. So any rational function, you can make it, you can transform it into canonical form, and the canonical form must have this formulation. Take this formulation. Okay, always. So that's why the solution of differential equation that with polynomial input, polynomial right hand side, always has solution as exponential, and also trigonometric function. Yeah, combination of those functions. And here is about transfer function. So by definition, transfer function G of S is the ratio between output and input. So in some sense, it's transfer inputs into something, okay, or response to the inputs. Okay. So as long as you can write down the ratio between output and input in a complex domain like this, then you get this one as a transfer function. Okay. So this one equal this times this. Okay. Something in the block diagram times the input. And again, you see initial condition must be 0. The next point is how to transform transfer function to state space representation. So from here, it's new. It can be new to you. State space representation, you're gonna see it. From from next lecture is. The next lecture I will introduce application of first and second order differential equation first, and then after that you will see the whole lecture is about state space. We use state space representation to describe system, and that is multivariable system. Okay. So from here it's very important because here is the introduction to state space representation, and so here I want to show how you can transform from transfer function formulation to state space formulation. There are many ways actually, but the first one is the easiest case. So from here you can cross multiply. So us times 24, ys times this polynomial. Okay. And then actually this one is obtained from is a Laplace transform of differential equation, right? So just rewrite it as differential equation like this. After that, we choose other variables. Now you have one variable, but you have third order, right? Third order of time derivative here. And state space representation of the system would be 3 variable, but first order. Okay? So first times 3, also 3 order in some sense, right? The way you choose state variable is like this. H1 is just y, and H2 is y dot. Okay. H3 is y double dot. Okay. So the first equation that you can create is the relationship between H1 and H2. So does H1 and H2 has some relationship? Yes. H1 dot equal to H2, right? You take this one dot, then it must be this one, right? This one dot, then it must be same as this one. So H1 dot is equal to H2, and H2 dot equal to H3. Okay. And then H3 dot must be, you take dot this one, then this one become dot one more dot on the y, okay, on y one more dot. So you have y triple dot. So y triple dot you can extract from here. Just move all of this to the right hand side. So you have y triple dot equal to something, right? And here actually y is just h1, y dot is just h2, and y double dot is just h3. Right? So now you have three equations with first order, but three equations. So still we call it third order. And for state space representation, you only write first order of derivative, first order of time derivative. But if you have three equations, you call it third order. You have four equations, you call it fourth order. Okay? The time derivative is always one. That is state space representation. And in matrix form, like this. I think I missed something. Yeah, I do miss something. Yeah, actually, h2 means 0, 1, 0 times h1, h2, h3, right? Because this 0 will multiply to h1, this 1 will multiply to h2, this 0 will multiply to h3. And add together, then you only have h2, right? Correct? Yeah. And for h2 dot equal to h3, this one times, yeah, this one, the first one times h1, and then this times h2, and then this times h3, right? So you just got h3 here. And this one is very easy. Minus 24, coefficient of h1, minus 26, coefficient of h2, minus 9, coefficient of h3. Very slow. So what I'm missing here? Yeah, actually this term, right? So I should have 0, 0, 24, and R like this. Yeah. And then the output, the original output of the equation here, original output here is what? Yeah, you inject input u. So it means you know value of u, then you solve this equation for y, right? Yeah, you solve this equation for y. So it means y is the output. You inject u, so you know the value of u, and you solve the equation to get y. So it means y is the output of the system. So output equation for state space representation, y is what? Y is h1. So you got 1, 0, 0 like this, because 1 times 2 is 1, and then 0 here times 2 is 2, 0 here times 2 is 3, right? So why do we write this form? Because the compact form would be h dot equal to a h plus b r. Oh, I made a mistake here. Sorry, I should change, because up here I use u. Up here I use u, and so here I should use u as well. U as input. Yes, here also u. So why I have r here? So I should add Control C plus Control V, 0, 0, 24 and use outside like this. Yeah, the compact form take this. Compact form is like this. H dot equal to AX plus BU. We call it state equation. And then output equation y equal to CH plus DU. So what is A? A is here, and this one is H, this one is H dot, right? H dot equal to AX plus this one is BU, right? And this one Y equal to this one is C, this one is H. So H here is vector. Vector 1 is 2 is 3, column vector, okay? You have question up to this? So again, this is very important, this formulation, the state space representation. You are going to see it again and again. Yeah, a lot, whole lecture for multivariable control system, multivariable control theory. How about du? Okay, du, actually d is just 0, right? Because y is just scalar, so d is just 0 times u. So you can have this formulation. So this is called a standard form of state space, linear state space formulation. Okay, linear state space. Yeah, I should say linear. Another way to transform transfer function to state space representation, but this case you have input not just u but also derivative of u. As you can see here, you have u dot and also u. If you follow the same process, you're gonna fail. You're gonna fail because the original equation here, I mean the standard form here, there's no the derivative term of u. See, there's no derivative term. So if you follow the same process, you're gonna fail. Then actually you can use a trick, which is to choose state as like this. So H1, H2 same, but H3 you choose a different way, right? So when you take derivative, time derivative on H3, then you got the derivative on u as well. This is the trick, right? So here it's yeah. So y double dot, yeah. So actually y double dot is y double dot here is actually H3 plus B0u, okay? Y double dot H3 plus B0u, right? And then H3 dot Y triple dot, okay, minus B0 u dot. So then you just manipulate, try to substitute all derivative of y into state variable E1, E2, E3. Just do some substitutions. Finally, you get the same state space form, linear state space. Okay, so you have h dot equal to ah plus bu. Yeah, u here already. And then you have y equal to ch plus du. There is another way to transform from transfer function to state space representation as well. Actually, this one can apply to this one as well, because if you look at the Laplace transform of this equation, you will have the transfer functions like this. You got b0s plus b1 over s cube plus a1 s square plus a2s plus a3. Okay, so if you know how to apply this one, then you know how to apply the same method for this equation. But this equation, you can have a different trick to choose state variables. I missed something here. Yeah, I want to discard b0. Oh, what is it? This one is b2, right? This one also b2. And this one okay. So in this case, first so you have input u, and then you just take the denominator. Yes, you split between denominator and numerator. Okay, this one is numerator. This one is denominator. Denominator. And so you choose state variable h here. Yeah, you have hs here. Then you choose state variable h1, h2, h3 to be okay. H1 is I don't have C here. Okay, so from the denominator you get h1, h2, h3, and this one is you look at this one, this part is just like identity. This part is just like identity because you start from 1 from the second and then 1 on the third. If you have another, if you have 4 variable, 1 will be here, 0 here. You see the trend? Can you see the trend? Because h1 dot equal to h2. Okay, we choose h1 equal to h1 dot equal to h2, and h2 dot equal to h3, okay, and h3 dot equal to, yeah, all of this like this, okay. And then the output y, you just choose b0, b1, b2 input in here, okay. Yeah, because h here, yeah, actually if you multiply h to this, you have like b2 h double dot plus b1 h dot plus plus b0 h, right? So it's like different, yeah, it's like the time derivative, it's just differential equation, right? Yeah, so that's why you can how to say, you can choose state variable h1, h2, h3 like this. Yeah, so h1 is just h itself, h2 is h dot, and h3 is h3 is yeah, h3 is h double dot like this, okay. Okay, and do you have a question? Because I think this one is a little bit difficult. If you can understand it, it's good, but if you don't understand, please ask, then I will explain more. So I just don't know which part I should explain to you. Okay, maybe I start from here first. Yeah, I think maybe it's not easy to understand it. I want to explain again. Then, yeah, actually I should say, in order to get this matrix A, actually I consider this part first, just only this. Yeah, if I consider this, actually US equal to hs times s to the s cube plus a2 s squared plus a1 s plus a0. Yeah, that's one you can have if you use a Laplace inverse. Then you have u of t here. This one is right? Correct? Okay. Then you use the same way as this one. Just use this process. Okay? This process you can get this matrix A and matrix B. Right? Yeah. And but then for y output equation, if we look at here, each time this one you get b2 h double dot plus b1 h dot plus b0 h, right? So yeah, but okay, so h1 is h itself, h2 is h dot, h3 is h double dot. Yeah, so you follow this process, you get this matrix A and matrix B, and then you look at this one, because this times this, you can have this. Just use inverse Laplace transform to write it in time domain, and then this h2 actually is just h3. Here is h3 and here is h2 and here is h1. That's why you have coefficient b0 times h1, b1 times h2, and b2 times h3. Okay, so you have seen 3 ways to transform from transfer function to state space representation. Alright, so here the summary of Laplace transform. I'm not going to explain it, I will skip it. So because now time is up, we're going to continue next week and do the practice. Okay, so I will try to have practice section as many as possible. Okay. Where? No. Yeah. Where? 00U. Okay, because equation, so h3 triple dot equal to minus a2 h double dot minus a1 h dot plus a0h, and here u, right? Because I move all of this to this side, right? That's why I got dot minus here. Oh, this one minus 2 minus, and I still have u here, right? This u. Yeah, a little bit slow. This u, right? So because other equation we don't have u, right? This equation no u, it means 0u. This one also 0u. But this one, no, not this equation, sorry. I need to take h1 dot equal to h2 plus 0u, and then h2 dot equal to h3 also plus 0u, right? And then h3 dot equal this one. So this one has 1 u, right? That's why we get this one 0, 0, 1. Yeah, just try to practice a little bit. Yes, just try to catch the process step by step in the right order, and then you practice a little bit, and you can get the final answer. Okay, so I will see you next week on Monday and Tuesday, right?